So in this session, we're going to talk about how galaxies can interact and collide with each other and cause some of those galaxies' features to be distorted and have different kinds of appearances. So that's kind of what we mean by peculiar galaxies. Earlier on in the course, we talked about how stars are very, very far apart from each other compared to their relative sizes. So for example, if you took our sun and shrunk it down to the size of a basketball, the next nearest basketball-sized star would probably be somewhere in Europe. So again, there's a lot of space in between those. And because these distances between stars relative to their size is very great, we almost never see collisions between stars, at least stars that are from different star systems. When we talk about binary star systems where they're already close together, sometimes those ones can collide. We'll talk about that at some point a little bit later on in the course. But stars between different galaxies, imagine that you had two people walking around in the US and they were just randomly placed in the US and just started randomly walking. It is extremely unlikely that they would ever bump into each other. In the same way, the distances between stars are so great relative to their sizes that they're almost never going to bump into each other. On the other hand, galaxies, compared to their sizes, are much closer together and can regularly collide and interact with each other, resulting in galaxies that have these kinds of distorted features. We said that for stars, if we took our sun and shrank it to the size of a basketball, the next nearest star would be in Europe. If we took our galaxy, which is again much larger than any star, our galaxy contains hundreds of billions of individual stars. If you took our whole galaxy and shrank it down to the size of a basketball, the next large galaxy, the Andromeda Galaxy, would be a little bit further away than the edge of this room. So again, even though, and I want to stress this point, galaxies are larger than stars. Galaxies contain many billions of individual stars. We're not saying that galaxies are closer together than stars are. We're saying that relative to their size, like how many galaxy widths is the next galaxy away from us, that relative size for galaxies is much smaller, so they're much more likely to collide. And again, when we have these galaxy interactions, we see these galaxies with very, very distorted features. Here's a galaxy with a disk that kind of got, bent in a weird way. We've got galaxies that have these wide dust tails kind of flying through each other. We've got galaxies that are interacting right now. We can actually see them at a specific point in these interactions. So we're going to talk just very briefly about some of these galaxy interactions. So here are two galaxies that are actually colliding with each other. So they're actually two galaxies that are running into each other, and we see that they're getting these very distorted features. Well, one thing that we can do is we can run computer simulations to identify, well, what would these two galaxies, what might they have looked like in the past? What will they look like in the future? These collisions of galaxies happen over very, very long time scales, hundreds of millions of years. For an example, for our sun to orbit once around our Milky Way galaxy, that takes about 230 million years. For these galaxies to actually come towards each other and collide and go through that whole collision or possibly merger process, it's going to take many hundreds of millions of years. But we can use images of these galaxies that are currently colliding and get snapshots of this is what this galaxy interaction might look like. And then we can use computer simulations to say, based on what we know about spiral galaxies, or spiral galaxies or elliptical galaxies or other kinds of galaxies, if they interact in certain ways, well, what sort of structures might we see? So this is a computer simulation. This is actually a pretty old computer simulation of two galaxies colliding in a way that would make this kind of a structure. So we've got two spiral galaxies. They start to run into each other, and then the gravitational forces that these galaxies have on each other are going to trap some stars, and other stars get kind of launched away in these long, what are called tidal tails. And we notice that these kind of tidal tails are pretty similar in structure to what we actually see in this colliding galaxy pair. So this is how we compare computer simulations of the full drawn out galaxy collision process and compare that with the features that we actually see in real galaxies that have either gone through a collision or are still in the process of colliding in these ways. This is another galaxy called the Cartwheel Galaxy that seems to have just had, let's say this is the spiral face of the galaxy. Another galaxy has come in and kind of smashed right through the middle of that. And let's see what this looks like. So this is the same galaxy looking in a range of different parts of the spectrum. So the purple light is the X-ray light. The blue light is the ultraviolet light. Green light is the visible light. And the red is the infrared light. So this is kind of trying to take an image of this galaxy and extend how much of the electromagnetic spectrum we can actually see. And we see a whole bunch of different features. We can compare that to a computer simulation of what would happen if a galaxy kind of punched through the face of one of these spiral galaxies. So let's take a look at this. We run the simulation, again, that smaller galaxy punches through the face, and then we get this shock wave starting to come out. When we talked about star formation, we said, well, if I have one of these giant molecular clouds, we need some kind of trigger event to start this thing going through gravitational collapse. And once it starts to compress a little bit, gravity will usually take over and compress the rest of the way, starting to form clusters of stars. Having another galaxy kind of punch its way through a neighboring galaxy, that's going to be a pretty strong event for triggering star formation. So this shock wave that we start to see, this is this burst of star formation happening. The camera does kind of a little swoopy thing around here. It kind of produces stars. Those stars start to form some massive stars that are going to go in supernovas, extending that shock wave. More stars, more supernovas, extending those shock waves. And we get this particular structure. Sorry, the camera's still doing a little kind of loopy thing. We get a structure very similar to what we see for this Cartwheel Galaxy. And there are, again, a couple of features that I really want to highlight with the original image. I'm going to go back away from that for a moment. That ultraviolet ring, that ring of ultraviolet light, we said that one of the strongest sources of ultraviolet light is that star formation, those relatively new stars that are going to be forming some O and B type main sequence stars, and those are going to be giving off a lot of UV light. That shock wave that seems to be going out from this from the center of this the disk of this galaxy, that's showing a lot of this ultraviolet light that is the signifier of lots of star formation going on. You'll also notice that we get a lot of these purple spots. You can see it more in this kind of cutout of the X-ray image. We get a lot of those purple spots showing strong X-ray sources. Well, one of the strong X-ray sources that we talked about were black holes. When this shock wave goes through the galaxy, a lot of that new star formation, some of those areas are going to produce very, very high mass stars that are going to go through their lives very, very quickly and end up forming black holes. Those black holes that are still in this gas-rich environment are going to start pulling in on some of those gases, producing that accretion disk. Those layers of gases are rubbing against each other, starting to heat up to the point where they start giving off their own X-rays. So these X-ray sources are very likely to be the accretion disks around relatively new formed black holes. So again, even though we can't directly observe in real time what these galaxy collisions are doing, we just get these snapshots, because again, these galaxy collisions would take hundreds of millions of years to occur. We do get these snapshots, and we can compare that to computer simulations of what we think would happen to see if we get a picture of how these galaxies interact in a way that is that matches up with our understandings of star formation, life cycles of stars, the sources of these different kinds of light, making sure everything matches up very nicely. So when these galaxies collide, remember, we said that stars themselves are very small compared to the distances between those stars. So when these galaxies collide, it's very, very unlikely that two individual stars will actually collide with each other. Because again, the stars are just going to kind of pass through each other like a sieve and not really interact. Remember how I said that if our sun were the size of a basketball, the next nearest star would be in Europe. Well, let's increase, how compact that is and move those closer together. Let's say there's like 10 people randomly placed in the US, give them blindfolds and tell them to just wander around. The likelihood that any of those people are going to run into each other is extremely small. Same way, these stars that in these colliding galaxies, the stars themselves are small enough that they generally just pass by each other. But larger clouds of dust and gas, those are going to collide, and those are going to produce huge bursts of star formation. Again, these are some of those images of galaxies that are in the process of colliding. And what are those signs of star formation? Those blue speckles and pink splotches, the blue speckles being the young O and B main sequence star, those pink splotches being the ionization nebulas that are being excited by those nearby O and B main sequence stars. And these ones go through that system a lot. There are these starburst galaxies, these galaxies that have just gone through collisions that can actually have such rapid star formation that they actually use up all of those galaxies' gases. They use up a lot of that gas in this intense star formation. And then after that intense star formation, you're going to have a lot of high mass stars that are going off as supernova in rapid succession. So it's going to use up most of the gas in forming those stars. And before that material can start being recycled, those supernovas are going to go off with such force that they eject any remaining gas, leaving very little behind. So depending on the exact conditions, you can have a couple of gas-rich galaxies, say spiral galaxies, that collide with each other, go through this rapid star formation and ejecting that remaining gas, and leave behind one of these elliptical galaxies. In one of the last sessions, when we were talking about the types of galaxies, we said that the giant elliptical galaxies that we find at the centers of large galaxy clusters, those may be the result of repeated mergers between galaxies in that tightly packed cluster. Well, this is a mechanism for which you're actually going to be able to make one of those elliptical galaxies out of many, many mergers. Let's look at another example. Here's two interacting galaxies. These are called the mice. And we have a computer simulation. Again, these are still pretty old computer simulations, but get the point across, where these two galaxies collide, and depending on exactly how their disks are oriented, their rotation rates, they can produce these long tidal tails where certain regions of stars are kind of ejected out in these long streaming lines, which is pretty much the same as what we get in a lot of these images. We see these long tidal tails, and based on the mechanics of these galaxy collisions, which we can test by using computer simulations and supercomputers, we can actually get a really plausible mechanism for how we would actually generate these types of structures that we see in these galaxies. Now, afterwards, these galaxies will probably continue to merge, and eventually we'll go through that rapid period of star formation and eventually leave behind this, what is probably going to end up being an elliptical galaxy. If we have lots of merging galaxies, well, there's going to be a lot of those gases in all those merging galaxies that are running into each other. It can actually heat up those gases to millions of degrees. Again, these are very, very thin gases, still a vacuum by, comparing with anything on Earth. But after repeated mergers, these gases that are constantly running into each other, going through star formation and forming more stars that are going to go supernova, producing more hot gases, they can heat up to literally millions of degrees and start emitting X-rays. So this is a bunch of galaxies that are all kind of partway through merging. These are all galaxies that are kind of piling up on each other. And if we look at those galaxies in the X-ray part of the spectrum, we see some of these very, very heated gases. The last thing that I want to mention is our Milky Way galaxy and the Andromeda Galaxy are currently on a collision course. They're not going to collide for a couple of billion years. Our sun will have gone through more of its life cycle in that time. But in the next few billion years, we know that our Andromeda Galaxy is on a collision with the Milky Way galaxy. There's a video on YouTube. I'll just leave the link here. I don't think I'm actually going to show the whole video in this session, but I do recommend having a quick watch. It's only about a maybe 4 or 5 minute video, but it kind of talks through how we know that the Andromeda and the Milky Way are on a collision, and talks in more detail about how our night sky might change over the next few billion years as our two galaxies start to merge with each other. Once again, it's very unlikely that our solar system will be directly affected by this merger because, again, the stars themselves are small enough that they are pretty much guaranteed to miss. It's a very low odds that our solar system itself would be disrupted. But our view of the night sky, we can see in the night sky the disk of the Milky Way galaxy. After this collision happens, it's very likely that we're going to have one larger galaxy that is an elliptical galaxy, so we won't have that nice spiral disk anymore. So this is just one of the properties of galaxies that we're going to be talking about. We're going to be talking more about galaxy formation, large-scale structure, active galactic nuclei. We'll be talking about some of those things in the next couple sessions.